Lecture 1, Intro to Computer Programming with Java Math 130 with yours truly, Professor Mimi Rasky. Let's talk about the rest of the programming process and troubleshooting. Stay tuned and be able to answer the following questions after watching this video. What are the 5 steps of the programming process, and which step is the one that students are most likely to skip? Which step is the one where students tend to get stuck? Will you always get an error message to tell you what's wrong while you are troubleshooting? And what's the difference between a syntax error and a logic error? Recall that a computer program is basically a solution to a problem, and you design the solution and run it, test it, troubleshoot it, and hopefully you get a great solution to your problem. The basics of a typical computer program involve 3 things: inputting data, then processing or manipulating the data, and finally outputting your result or solution. And recall from the last video that an algorithm is simply a recipe, a set of step-by-step instructions that a computer can follow that will ultimately find the solution to a problem. Now, finally, let's talk about syntax. Key word there, syntax of a language. Each high-level language has its own syntax or rules about how language elements are combined correctly to produce usable statements. For example, depending on the specific high-level language, you might use the verb print or write to produce output. And all languages have a specific limited vocabulary, and these are known as languages keywords. In addition, a specific set of rules for using that vocabulary. So you're basically learning a new language when you learn a new computer programming language. Using a programming language, programmers write a series of program statements similar to English sentences to carry out the tasks they want a program to perform. Program statements are also known as commands because they are orders to the computer, such as output this word or add these 2 numbers. Now let's talk about compiling versus interpreting. After you write your computer program, you're going to want to compile it. And a compiler is a software program that translates your language into machine language. Recall machine language from last time, 1s and 0s, which is the only thing your hardware is able to understand. And a compiler translates the entire program before carrying out any statements or executing them, whereas an interpreter translates one program statement at a time and executing that one statement as soon as it gets translated. So whether you use a compiler or interpreter depends on the programming language you use. For example, C++ is a compiled language, but Visual Basic is an interpreted language. The benefit from having a compiled language is they execute more quickly, whereas interpreted languages can be easier to develop and debug. Now, Java is sort of a hybrid between those 2. It uses the best of both technologies. It has a compiler to translate your programming statements and an interpreter to read the compiled code line by line when your program executes. Executing your program while it's executing is called runtime. This is just a picture that does say it all when you're trying to troubleshoot your program. You'll try and compile and run it, and you might get 1 error, and you'll say, yay, 1 error, that's it, and you'll fix it. And then all of a sudden, you'll compile and run your program again, and you'll get 927,234 errors. Well, that might be a little bit of an exaggeration, but sometimes not so much. You'll find out why this is so funny maybe later on. Let's talk now about errors in debugging. Compilers and interpreters issue 1 or more error messages each time they encounter an invalid program statement. That is, a statement containing a syntax error or misuse of language. Let's talk about some examples of syntax errors. Misspelling a keyword, omitting a word that a statement requires, and my personal favorite, you will run into this one more often than you like, accidentally using a colon when you're supposed to use a semicolon. I've done that one a million times, and I'll probably do more in the future. When a syntax error is detected, the programmer, that would be you, can correct the error and attempt another translation. Repairing all syntax errors is the first part of the process of debugging a program. And debugging means freeing the program of all flaws or errors, which are also referred to as bugs. Let's talk more about errors in debugging. Believe it or not, it's totally possible to write a program with correct syntax that still contains logical errors. In other words, just because there are no error messages after running your program, you may still have to do a lot more debugging. A logic error is a bug that allows the program to run, but that causes it to operate incorrectly. Correct logic requires that all the right commands be issued in the appropriate order. And here's just some examples of logic errors. Multiplying two values when you meant to divide them. Producing output prior to obtaining the appropriate input. And there's many, many more. When you develop a program of any significant size, plan out the logic before you throw down your code. Correcting logic errors is much more difficult than correcting syntax errors because often they are not accompanied by error messages. Often you can identify logic errors when you examine your program's output. For example, if you know an employee's paycheck should contain the value of $4,000, but your program's output, you see that the payroll only has $40, then a logic error has occurred. You need to fix it. One more key fact about debugging your program. Let's say you got rid of all the syntax errors and you think you got rid of all the logic errors because your program is looking like it produces correct output. For example, you suppose your program is supposed to multiply two values entered by the user, and the user enters two 2s and the output is 4. But since 2 times 2 is 4, but so is 2 plus 2, the program might actually be adding those values by mistake, but you think it's running fine. So the programmer would discover this logic error only by entering different values, such as 5 and 7, and examining the result. And this is why testing and running your program over and over with different test data values is very important. Let's talk about the 5-step programming process now. Step 1, define the problem. Clearly define what the program is to do. Or if you're doing one of the homework assignments or labs in this class, read over that homework specifications, which is specs for short, for your assignment. Number 2, plan the solution. Now this step involves visualizing the program running on your computer, and that might involve modeling. For example, let's say you're doing a payroll program, then your code kind of has to model a bank. And you're going to write desk code, which is sometimes called pseudocode, and sometimes you might use flowcharts during this step. Let's talk about pseudocode. Pseudocode is defined as detailed yet readable description of what your program or algorithm must do, expressed in English or Spanish if you prefer, but not any computer code. Also, please do not just throw down code. Let me tell you a quick story about skipping this second step. The professor of computer programming over at San Diego State told this story to the class. He took a team of San Diego State computer science majors to a computer science competition that was a national competition, and they were competing against some very, very good schools, Ivy League schools. And it's about a 5-hour competition, and each team is given the specifications, and they're supposed to read through it, and within the 5-hour period, come up with code that works. Well, the Ivy League school did not do this key second step. Instead, they kept throwing down code and not getting the answer they were hoping, and then rewriting, recoding, running it again over and over. Well, San Diego State was a little bit more savvy. They did plan their solution. They used pseudocode, and they made sure they had their solution down on paper before they started throwing down code. And so, guess who won? San Diego State. So please don't skip this all-important step. Another thing you can do during this step is drawing flowchart diagrams, which is a very helpful tool. We'll discuss that in a little bit. Step 3, make sure you code your program, and that's the step where you just type up your code. But be sure you do it in a piecewise fashion so that you can troubleshoot and test each piece separately. Some of the lab assignments I might give you are extremely challenging because they're a little bit long. If you just throw down all your code and try to do everything all at once, it might be kind of troublesome. Instead, write a little bit of code, just a few lines, make sure that works properly, and then add a little bit more, and so on. Number 4, test the program. This involves compiling, running, and troubleshooting your program, as well as coming up with data to test your program. And the purpose of testing is to find defects, not just to pass easy tests. You're going to need to correct any compilation errors, which are also known as syntax errors, as well as runtime errors, which are also known as logic errors, that are occurring while running your program, as well as any errors in your results. And this is the step where students tend to get discouraged or stuck. You will most likely have to repeat steps 3 and 4 as necessary. And be sure and validate the results of your program. That is, make sure that all of your output matches what you intended. And finally, number 5, document the program. Documentation can be done by commenting your code, which we're going to discuss later, or using the JavaDoc tool, which we're not going to use in this course. Finally, the warning here. It's very uncommon for programs to run the first time they are written, even for me, so be prepared to do steps 3 and 4 repeatedly. Here's a flowchart diagram right here about the programming process itself. So at the very top, you have this rectangle that says what you'll do first. So you're going to follow the arrows, this flow chart. Here's the flow. First, plan your program logic. This is the step where you're going to use your pseudocode. Okay, after you do that, then you're going to write your program language. So you're going to type up your code. Then you're going to compile or run it. And if it compiles successfully, great. Drop through, but usually you're going to have some syntax errors. You're going to go over here, you're going to look at the list of all the syntax or error messages that are going to show up, and then you're going to come back around and fix those errors. So in other words, you're going to be doing this loop, if you will, as many times as you need to until your syntax errors are debugged. Then you can come through and execute your program, and hopefully you will get some output or result. Now here is where you're going to look at your output. If there are still some errors in what you were hoping to get, yes, you're going to swing back around and come all the way back to the top, yes, square one, and plan your program logic and recode it and so on, which again, you may have some more syntax errors showing up. So another loop that you may be coming up with that is the second part of the programming and troubleshooting debug is this loop right here, the big one, the outer loop. So you're going to do the outer loop and the inner loop as many times as it takes until you're done. And then afterwards, please remember to validate your program, even though there's no box down here, as well as add your documentation. Don't let this be you. Let's talk a little more about troubleshooting and testing. Troubleshooting can be very time-consuming, thought-provoking, and patience-trying. Try not to get too discouraged. Coming up with a full range of testing data, that is what's known as a testing suite, can be a challenge. And I've had a student whose output was perfect in his assignment, and I still did not let him pass that assignment because he did not look at all the different possible data that the code could have. And so he only coded his program for the output that I showed. He didn't think of all the possibilities. Receiving error messages when you run your program is a good thing. You may not think so, but believe me, it's great. At least you have an idea of what to correct. If you don't get an error message, and you may think, oh, that's great, but that's way more challenging to troubleshoot because those are the logic errors. And there's two types of those errors that come with zero error messages. One, it compiles and runs, but doesn't give you the results you intended. Worse, it compiles and runs for a while and then crashes your computer. That's very bad. Here's a breakdown of your programming time for each assignment. Believe it or not, your debugging is about 70% of your overall time. Most students think this is backwards, that most of their time is going to be spent typing up the code, but that's not true. Moral of the story, don't be too upset if the majority of your time is spent troubleshooting and testing and debugging your programs. It's totally normal. Although I did have one student a few years ago who he spent his entire weekend debugging his code, and most of that time was spent finding actually what turned out to be a very easy error, and he told me he wanted me to refund his weekend back. I'm sorry, I can't do that. Troubleshooting may involve discouragement. It can sometimes feel like you're trying to connect the dots and you don't even know where the next dot is, much less what the image is supposed to be. So just hang in there and be patient with yourself. You may want to even go to the tutoring centers, and we have some very good tutors there. And you come to my office hours when you get really stuck. But when you finally get your code to work, this is going to be you. It's going to be all so worth it. So we'll see you in the lab.